Hello, my name is Matthew Nealon. In this video, we'll be deriving an equation to use in our Python code later on in part 2 of three tanks that are separately filling each other up. So before we start with our triple tank problem, we're going to go and just represent some variables that we want in just a single tank to understand what's going on with all of our tanks here when we eventually go to our third tank problem. So what we want to do is set up a tank here as such. Just a simple tank that has some unknown fluid in it, that has some concentration of some liquid in it. And then what we want to do is add just a little stir. And this is just going to be an assumption we have that this whole system is well mixed. And what this well mixed thing means is that that the concentration throughout the entirety of this tank is uniform, or it is the same concentration all throughout. Then we can derive another unit. Is our fluid level, which we'll derive as H, or fluid height, one would say. Another thing we can derive just with this equation alone without adding any more is our cross-sectional area. And since this is a tank that has volume, you will have a cross-sectional area that be represented with the variable AC, which is our cross-sectional area up here. So then we'll start to add various changes to this tank. So first off, we want to add an input or an inlet, which is going to be derived as our Qin. And from here, we then want to derive an output or an outlet, because if no outlet existed, our tank would fill indefinitely and then overflow. So then we will describe our outlet as Q out, or the rate in which liquid is flowing in and out of our system. So we have some various units we can derive for Q in or Q out. So a unit that we can derive from this is that this top part is the volume of liquid flowing in. So we can then put that in meters squared per second. And that is the same of the rate flowing out. However, there's one more thing we need to consider here, is that there's concentration involved. Since this is a well-mixed mixture, we assume that concentration is then involved in this equation. So we have a flow rate or a concentration of the inlet, because we don't know the concentration of the water or some fluid being pumped into the system. We don't know the concentration of it, so we simply derive it as our concentration of A going in, and we derive it with our kilograms over meters cubed. And we can do the same down here, and we have our concentration of the liquid in here going out. However, since this is a well-mixed mixture, and since this our Q out, or our rate flowing out, or the liquid flowing out of our outlet, is just going to be the concentration that's already current in the tank itself. So we can assume that our concentration of the outlet, or the water flowing outlet, is equal to the concentration within this set tank. And with all of these variables then defined, we can start to derive some of our equations here. So then we can then set our equation as such, since we're trying to find the rate in which our fluid, or we're trying to find the rate in which our volume is flowing out first. So we can just derive our slope, or the rate in which our volume is decreasing, or our volume is changing in respect to time. So dV over dt is a good representation of that. And from here, we can then assume one other thing. We can then assume that we can use some of these variables up here. So what we want from here that represents our volume is our fluid level and our cross-sectional area from here. So we can assume that our height is changing, being multiplied by our cross-sectional area. And since our cross-sectional area isn't being part of the derivative here, it's because our cross-sectional area will be constant throughout the tank. If it goes up, the cross-sectional area stays the same. If it goes down, the cross-sectional area stays the same. So our H here, or our fluid level, is what is is one of our dependent variables, and AC, or cross-sectional, or our fluid level, H, and our cross-sectional area, AC, is our, just basically is going to be used as a constant. And we can then assume that our flow rate going in minus our flow rate going out is how the volume is changing throughout this system. And then we can start to derive some of our other equations, or try to find a relationship how this whole equation works. And there's one little thing I forgot to mention, is that this equation can then, or this Q out system is then, or our flow rate going out, is equal to another equation, which is our alpha times the fluid level to the 1/2. And our alpha is just a proportion that exists between our tank and the height. And our H and our fluid level value is being used as a square root. So then we can separate some of these things off now. So we want to, first off, let's just take this equation in terms of our change in fluid level. So we can then set up a new equation as such, which is our change in fluid level is equal to our cross-sectional area, since we're going to take this cross-sectional area and multiply it to the other side, times our inlet flow minus our outlet flow. And since we have this next equation here, we can then substitute what we have from this equation into our outlet flow. So we will then write this as alpha to the 1/2. And this represents our change in our fluid level. However, there's one little thing we haven't mentioned yet in this equation, is that what is our change in concentration as our fluid levels change or go up and down, dependent on all of our inlets and outlets, and our intake flow and our outtake flow. So we can then set up a new equation. We can basically set up a representation of this equation of concentration, which will then be used or derived as our change in excuse me, our change in concentration of the tank multiplied by H over dt is then equal to 1 over cross-sectional area multiplied by our inlet flow multiplied by the concentration of the liquid flowing in, so it's multiplied, minus our alpha value to the square root of our fluid level multiplied by our concentration within the tank currently, since our concentration out is the same as our concentration of the tank. So then from here, we can then derive this a little bit farther. Since we have two derivatives up here, or we have two variables up here, we can then use the product rule in calculus to then separate this left-hand side of the equation out even farther. So what we want to do, sorry if that's a little hard to read from the light, I just noticed that. What we want to do from here is then use our product rule. So we can then set up an equation such as the change in concentration multiplied by our fluid level over our change in time plus our derivative of our rate of change of the fluid level multiplied by our concentration of the tank here. And that will be set equal to our equation up above. So let me just rewrite this real quick. a little hard to write when there's such low board. So this will be, this is a good representation of what we have right now, but we can simplify this portion a little bit further. What we can do here is then, simplify this portion, our left-hand portion of the equation even farther by just having our rate of change of the concentration over time just all on the left hand. So what we want to do is just have our rate of change of concentration is equal to our 1 over our fluid level, since we have to divide this over. But before we divide this over, we're going to subtract this whole our change of fluid level over time multiplied by the concentration of the tank first, before we divide by 1 over our fluid level. So then that will have a bracket here to represent that. So we will then have our cross-sectional area, and then we'll just repeat this whole equation up above here. So then we will then have our flow rate going in times our concentration of the inlet multiplied by our alpha value multiplied by our fluid level, or square root of the fluid level, times our concentration of the tank. And that will then have our DH value, or flow rate, or this value here, these two values here, so then be our rate of change of the fluid level in respect to time multiplied by our concentration of the tank. And that is our whole equation, that is in respect to our concentration of the tank. And if you notice something here, is that we have another DH into this equation. So technically we could substitute this variable out for what we have up here. But we're not going to do that because it's going to get very, very messy if we continue to expand this farther and farther out. So what we can do, so we're just going to stop here. And this just represents our individual variables within one tank. All the things we have to look out for, especially when we're starting to include portions of our tank. What we want to do here, sorry about the cut, the light was a little too shiny and it was starting to mess up my work here. So then we can start using our 3-tank model. So 3 tanks we want to set up here are such as follows, where we have 1 tank, another tank, and a 3rd tank. And all of these are flowing to one another, starting with tank 1 all the way to tank 3. And then, so we'll just get rid of that as such, that as such. Just to set this up, easy to see. So we'll have a flow rate going in, and then have a flow rate going in, and then have a flow rate going out. And then for this particular equation, we have an inlet actually going into our second. We actually have an inlet going into our second equation of, or second tank here. So we'll just label this as tank 1, tank 2, and tank 3. So we have a rate going in. And one thing we can also assume that all of these tanks have is that we have a cross-sectional area of 1, a cross-sectional area of tank 2, and a cross-sectional area of tank 3. And we also assume that there's some fluid height that's not all the same in between our tanks as well. So we'll just set this as our fluid height of 1, set the second one as our fluid height of 2, and set this third one as our fluid height of 3. So we now have our tanks. So what do we want to do from here? As you notice, we have three rates going in and out of these out of these tanks here, we have a rate going from 1 to 2, from 2 to 3, and then 3 going out. And if you remember that our equation for our equation going out originally is going to be our flow rate going out is going to be our alpha value. And since this is the third tank, we want to separate this equation off. So we're going to say our third alpha value multiplied by our height value of 3 to the square root. So we then have our rate of 3 going out. So then we can then set up the rest of our equations and find a relationship between how our flow goes from 1 to 2 and then 2 to 3. So we can then set this up as such. So we have a representation of our first flow, which is going to be our flow to 1 to 2. We can just take this in terms of this. So since we have two heights, but we have a proportion or alpha proportion, which is just a proportion between tanks, between our heights and our alpha is just going to be a proportion between the height of our tanks. So we can just assume that, or we can just derive or set this original alpha value for tank 1 to 2 as just alpha 1, since we're going to have another alpha value for the second tank. And we assume that's going to be our H1 minus our height, our fluid height of 1 minus our fluid height of 2. I apologize if I wasn't saying fluid height throughout all of that, to our square root. But you might be thinking, well, what happens if our height, our fluid height of the second tank is too big? What would happen then? This would be negative, but we need a better way to represent that, because this would then not be a proper flow if we had some outstanding givens. If our fluid height of our second tank is higher than our fluid height of our first tank. So we want to expand this equation out a little bit farther. So first we then want to set this as our alpha value of 1 to the absolute value, our flow rate from 1 to 2. Within our absolute values is going to be the fluid height of 1 minus the fluid height of 2, end of absolute value, to the square root. And this is a good way of representing how the relationship of our heights between tanks 1 and 2. But there's one thing that we kind of forgot up in this first equation here, is that what happens if our flow rate is negative, or if our flow rate starts to go back the other way because the force, or if our values are a little too strong going the other way. So we have to then account for that. So our flow rate of going 1 to 2 is then equal to the sine of our fluid height minus our fluid height of tank 1 and our fluid height of tank 2, multiplied by our alpha value of 1 to the absolute value of our fluid height of 1 minus our fluid height of 2 square root. So this is a whole representation of just a relationship of the flow between our tanks 1 and our tanks 2. So what we want to do here is then figure out our flow rate between 2 and 3, which is going to be a very similar equation to what we have here. So what we want is we're just going to repeat that again. So it's just going to be our flow rate from 2 to 3 is equal to the sine of our fluid height minus our fluid height of tank 3 to the alpha value of 2 and the absolute value is our fluid height of 2 minus our fluid height of 3. And this represents, just to draw some arrows here, this represents that, and this represents and this represents that flow. So we have our flows here, but we now want to take this in terms of our volume values, since we have our flow rates, but we need to put this in terms of our volume values now. So we then have our volume values as such, since we wanted to separate off our volume values from the original equation, such as our change in fluid level over our change in time multiplied by our concentration, or not concentration, excuse me. We don't want concentration just yet. Our cross-sectional value is then equal to the flow rate, to our individual flow rates. So we want this, since we want excuse me, I'm trying to go my words here. This whole expression here is going to be equal to the flow rate that is going in and out between, or is going in and out of each of our tanks. And since there's only one flow that's happening in our first tank, it's just going to be a negative. It's just going to be a negative flow from 1 to 2, because there's no inlet value that's coming in here. Because technically, our flow from 1 to 2 is acting as an inlet to our tank 2, but an outlet from our tank 1. So just to make sure we don't get this confused here, we're going to separate this off as our cross-sectional value of 1 for this first equation, and our change in fluid height of 1. And next we have our tank, and we have our second tank, which then we can derive as this, as our change in fluid height of 2 over our change in time multiplied by our cross-sectional area of 2 is equal to 2 inlets. So our inlet values are going to be positive. So what we want here is that we want our inlet values. So we have our inlet from here, our flow rate in that's being generated, and then we have our inlet from our our first tank. So then we'll have that our inlet plus our inlet from 1 to 2 minus our flow rate out of our tank, which is going from 2 to 3. So we'll have our 2 to 3, our flow from 2 to 3 as our negative value. And then since we have one more tank we have to derive, we will then set this as our flow rate, our fluid height of 3 in respect to time multiplied by our cross-sectional area of 3 is then equal to our positive value, our inlet, which is going to be our flow rate from 2 to 3, minus our outflow, which is going to be our forgot to say that's just Q3, our flow of 3 going out, which is going to be our flow of 3 going out. But the last thing we need to do here is implement a controller, or a proportional controller, in this top portion here. In the original problem, it said we wanted a proportional controller for our tank 3, but since our flows, our flow from 1 to 2 is going to be temporary, because we're going to end up falling, not going to have enough water in our flow tank here. We can't rely on this as a steady source of water, but the one thing we can rely on as a steady source of or liquid or intake is our intake or inlet from our tank 2. So we can then derive it as, or we can then make a proportional controller as such. So we can say that that we're controlling our intake flow to directly affect both, we're using our intake flow to directly affect the volume in this equation here. So what we want to do is then set that equal to Kc, and Kc is proportional gain. Kc is proportional Kc is just a value that represents our proportional gain between tanks 2 and 3, and we want and since what a controller will do is that a controller will set a set point in our tank where it says we do not want to go either above or below a certain value in our tank. So then we will then set it as such. So it's going to be the fluid level in our tank and the set point minus our height of 3. This is our controller because we want to find the proportion between our two tanks and then the difference between our set point and our proportional. We want to find the proportion between our two tanks and the set points between our fluid level of or fluid set point of 3 minus our actual set point, or minus our actual fluid level in 3. And we can use all of these equations we just used now in our Python code, and then use that to integrate and use it later on to then figure out what the concentration and what our various volumes are and how they're changing throughout each tank as they flow from 1 to 2, and then having our inlet affect 2, and then 2 to 3, and then 3 flowing outward. We can then find all 3 of our volumes.